Hello, and welcome to another digital differential equation video for Salt Lake Community College. In this video, I would like to continue going through Chapter 4.5, Variation of Parameters, and look at the derivation of this method. So deriving the variation of parameters method. This corresponds to page 37 in your guided lecture notes. The method of variation of parameters applies to second-order linear non-homogeneous DEs of the form y double prime plus p of t y prime plus q of t y equals f of t, where our coefficients need not be constants any longer. They can be functions of t. To apply the variation of parameters, we must first find two linearly independent solutions, y1 of t and y2 of t, that correspond to the homogeneous DE, and then write the general solution for YH as C1Y1 plus C2Y2. This portion of our derivation will agree with everything we did in Chapter 4.4. Now, the variation of parameters technique is used to find the non-homogeneous solution, and it can be thought of as a perturbation method, where to find the solutions to where we first find the solutions to the homogeneous DE and then perturb them to find the solutions to the non-homogeneous DE. And we do this by replacing the constants in our homogeneous solution with unknown functions v1 and v2, which tells us our particular solution will be something like this. Here, it's our goal to find v1 and v2 that make this be a particular solution. That's what our goal is going to be. Now, how I do this should seem familiar to you, because we're proposing this as a solution. This is our proposed solution. And if this is going to be a solution, it has to satisfy the DE. So we're going to evaluate the DE with this solution by plugging it in for y double prime, y prime, and y. The way we're going to do this, let's organize our work a little bit. If this is yp, let's first find yp prime. And when finding yp prime, you want to know that v and y are all functions of t. So when we write this proposed solution, we want to identify that these are all functions of t, and so the product rule applies. So here, yp is going to be the derivative of the first is v1 prime times y1, plus the derivative of the second is y1 prime times v1. That, so far, is the derivative of this term. Plus, the second one is v2 prime y2 plus y2 prime v2. And that'll be the derivative of this second one, the second term. Now, in our derivation, we are going to choose to let some of these terms be 0. Here, we're going to choose that v1 prime y1 and v2 prime y2 are equal to 0 when you add them together. So that yp prime becomes just y1 prime v1 plus y2 prime v2. What I'm doing is I'm grabbing the terms that were not 0. I'm grabbing these two terms. So that's now what yp prime is. And if that's yp prime, let's now go find yp double prime. Again, we have to use the product rule when finding our derivatives because y and v are both functions of t. So the derivative of the first term is going to be y1 double prime times v1 plus the derivative of the second is going to be v1 prime times the first y1 prime. Plus, we'll take the derivative of our second factor now, or our second term now, is y2 double prime v2 plus v2 prime y2 prime. Now let's evaluate the DE. So remember our DE was y double prime plus py prime plus qy equals f of t. So y double prime is what I have first. It's going to be y1 double prime, v1 prime, v1 prime, y1 prime, v2 prime, or there's a lot of writing here. That should be y2 prime. v2 plus v2 prime, y2 prime. This is all your y double prime. Plus p times y prime, which we have here. So y1 prime v1 plus y2 prime v2 plus q times your original function, which we said is v1 y1 plus v2 y2. It looks complicated, but I'm about to simplify this. So now let's regroup terms containing y1 and y2. And there's probably lots of ways you could imagine me doing that. What I'm trying to say is, let's grab the ones that have the y1 double prime. Let's grab these ones. Let's grab this y1 double prime term here, this y1 prime term here, and this y1 term here. Of course, you're going to have to distribute the q and the p when doing this. If you grab these three terms, notice all three of these terms. Oh, and I've got an extra derivative here. There shouldn't be a derivative on that. Okay. All three of these terms have a v1 on them. A v1 with no derivative. So I'm going to regroup these three terms, and I'm going to also factor out that v1, which means I can write them as v1 times y1 double prime p times y1 prime plus q times y1. Okay. I'd like to do the same thing. I'd like to grab this term with the y2 double prime. This term, we'll have to distribute the p. And this term, we'll have to distribute the q. When you look at these three terms, notice that they all contain a v2 term with no derivative. I'm going to regroup these and factor out the v2. So I'm going to have y2 double prime, p y2 prime, q y2. After doing that, what's left over is this term and this term. So I'm going to group those together. v1 prime, y1 prime, v2 prime, y2 prime, and this all has to equal f somehow. Now, what you would like to notice here is that our first grouping is our differential equation that was given to us, evaluated at y1. But remember, y1 was a homogeneous solution. And if it's a homogeneous solution, it means that all of this will end up being 0. That's what the definition of our homogeneous solutions are. Similarly, on our second grouping, y2 is a homogeneous solution. It means that all this has to be 0 when I evaluate it at y2. All that's left over then is these last two parts. Now from here, I want to write a system of equations. My system of equations will contain this equation and our initial proposed particular solution. So let's grab these two functions. Oh, not that one. This one. I want to write a system of equations with these two equations. So we try and group this together nicely on the next page. Let us now write a system of equations as follows. From our first one, we had v1 prime y1 plus v2 prime y2 equals 0. And from our second one, we had v1 prime y1 prime plus v2 prime y2 prime, and this had to equal f. As a matrix equation of the form ax equals b. Now, to write this as a matrix equation, what I want to do is factor out the v1, v2 primes. If I factor these out, I can write our system of equations like y1, y2, y1 prime, y2 prime times v1 prime, v2 prime equals 0f. So this is our system of equations written as a matrix. Now there's lots of ways we can solve this system, but I like using Cramer's rule. Now remember, with Cramer's rule, we can find a value for each of our solutions one at a time. So let's first write a solution for v1 prime. v1 prime, this is going to equal, remember Cramer's rule says it's the division of two determinants. The determinant of the bottom is your original matrix. And the top is going to be a matrix obtained by replacing the first column of your matrix A with your right-hand side. Similarly, let's write an expression for v2 prime. v2 prime can be written as a division of two determinants, where your bottom determinant is your original matrix, and your second column is replaced with your right-hand side. Now, what you'd like to notice in this derivation is that your denominator should look like the Wronskian of your functions y1 and y2. So when we actually write our shortcut for finding our solutions, we write v1 prime as a division by the Wronskian of y1 and y2. Now for the numerator, let's actually do the determinant. Because this is a 2 by 2 determinant, you use the product of your main diagonal. 0 times y2 is 0, minus the product of your off diagonal, which gives you a negative y2 times your forcing function. For v2, you have the product of your main diagonal minus the product of your off diagonal, which ends up being 0. So you just get y1 times f. These are the two formulas you need to know in order to find expressions for v1 prime and v2 prime. However, in our solution, you now need to integrate to find V1 and V2. Then you can write the non-homogeneous solution as YP is V1 Y1 plus V2 Y2, where Y1 and Y2 were your homogeneous solutions, and V1 and V2 are the solutions we just found using the variation of parameters technique. We could then say that our general solution would have to look like Y of t is C1Y1 plus C2Y2 plus your V1Y1 plus V2Y2, where this portion here is always your Y homogeneous, and this portion here is always your particular solution. Okay, I hope this is helpful, and I'll see you in our next video.